Engineering 305. This is a quick video, maybe not so quick, which is going to give you some additional help with finding I, that section modulus. The problems really around beams become identifying the geometry, and we've already kind of pointed it out. I pointed it out in the first lecture. We didn't struggle with it, but we were messing around most of the example problem with finding I, and so I want to spend some more time talking about that because there are a lot of tips and tricks, and so having some experience will help. So the things we're going to cover really is the first thing is just the equations, or the equation, which is really I is equal to base height cubed over 12. The second thing we got to cover is parallel axis theorem. And that is you're going to add plus the area times d squared. Look at the units. Look at the units. The units match up. It's going to be in units of length to the fourth. And then I want to really talk about just creative solutions. What do we do in certain situations? How do we solve the problem? How do we think about it? So there you go. So we've got those things going on. So I left the problem figure from 7.2. I left that up because we used in 7.2 we used this I equal to base height cubed over 12. But then we did this second shape. We did this second shape where we had this outside minus the inside. And since those they have a shared axis, shared neutral axis. And honestly, that's the first thing that maybe we should be talking about is this neutral axis, because the first thing you've got to do is figure out where the centroid of area is. That's one of the things we didn't go through in the proofs that show up in section 7.3 and 7.4. is that this neutral axis, the centroid of area, is where this bending takes place. Okay, so once you've found that, if you have a shared neutral axis, then I for the difference is just equal to I for the whole, or the outside, minus what you subtract, minus that subtracted area. And let's get that to a spot where you can see it and get rid of that and get rid of the equations. And we're going to use that quite a bit. We're just going to subtract that. I guess maybe I should have wrote that for I for the whole minus the red minus I for the subtract, just to get my colors right. But we're also going to get another situation where it's very common that, and this gets us to the parallel axis theorem, is they're going to give us a shape that consists of this plus that lump at the top. Now, the beauty of this normally is it's pretty easy to find the neutral axis because you're just doing two areas. So if I said this is a 1/6 and a 1/6, well, the centroid of this is 3 inches up, and the centroid of this is 6.5 inches up, and it's just going to be the average of the two. It's, if you recall, because you got to go way back in your calculus because we've done this, it would be a weighted average. So it's the 6 times, which is the area times the height, the 6.5, plus the 6 times the 3, all divided by the total area, which is 12. And so let's see, this is going to be 39 plus 18 divided by 12 equals 49, 57 over 12. and that's going to be a little less than 5. It's going to be 4 3/4, 48, 9, 4 3/4, which is just the average of 6.5 and 3. That's 1.75 from there, and then 1.75. Yeah, 4 3/4. So there's my new axis. There's my new axis. That's my axis that I have to worry about. So now to find I, what you're going to get is it's equal to I of the base plus the area of the base, and then the distance that the base shifts. Distance the base has to move. And that's just for the lower part. And then you got to do the upper part. I for the upper plus area of the upper times the distance that has to shift. Now, because my areas were the same, my shift, D for both, D for the base, the distance the base has to shift is equal to 1.75, and the distance that the upper has to shift is equal to 1.75. So that's fairly straightforward. I is equal to I for the base. Well, let's just start writing it out. The base is 1. The height is 6 cubed. That's a big number. Divide that by 12. Plus the area is 6 times the distance. Oh, I forgot a squared. Where's my team? You guys got to help me out. 1.75 squared. Plus I for the upper is now 6 times 1 cubed divided by 12. Plus the area for the upper is the same, and the distance that the upper has to move is the same, not a plus. 1.75 squared. Now, what I want you to see is that term is the same because the area is shifted the same, because they have the same area and they shift the same amount. So that, but this term is huge compared to this term. This term is equal to a half, right? 6 divided by 12. This term is equal to 6 times 6 is 36 times 6 is 180 is 216 divided by 12. I don't even know off the top of my head. That's not in my standard tables. Hold on. Here, I got it. 18. I mean, that is just so much. This just totally dominates. Totally dominates the system. This 6.175 squared, if I just say that's equal to 4, this is equal to another 24, so that shift is big. So this causing me to shift the axis up makes that a big deal too. So that's important. But I just want you to get a sense of how those things contribute. The fact that that's there laying horizontal doesn't do much, but the fact that it's got that shift, that's a big deal. So really what you're seeing is 48 plus another 18. So you got a total of 56. Wow, that's pretty big. That's pretty big. You know, that would be okay, let's keep going. Let's keep going. That's something to talk about. We'll have to investigate that in a minute. But then let's talk about another shape, and that, or let's talk about another way to do this, and that is sometimes we just need to get creative. We just need to think about this a little bit differently. One of the ways that can happen is, and a common shape is going to be this I-beam. And let's flesh this out a little bit so it has some shape. Let's get rid of this, just a single, and put this down here. And I think you might see this in your homework where, let's say this is 2 inches wide here, and this total, let's just make this and I know I didn't draw it to proportion, but make this 6 inches wide. So these are made by 2-inch wide by 6-inch wide pieces, 2-inch tall by 6-inch wide or whatever. So these are all, and those are not 2x6s, by the way. A 2x6, when you buy lumber, it's dimensionally undersized. Professor Nielsen always stressed that. But what you get when you do that is then this zone here is 2 inches by 6 inches, and this zone here is 2 inches by 6 inches. Well, now you've got a different way of solving it if you look at it. If we're trying to solve for IX, this has this a neutral axis here, and I've got a different way of doing this. Let me draw. I'm going to use colors to denote things. IX. See this black zone? Is equal to IX minus 2 times I of that X, which is just this. So this is just IX for the red. We're just going to use one of them. But if I calculate that, then that one's just the same. And this makes this problem really easy. Instead of doing parallel axis theorem and moving this shape down here, I can simply say equals base is 6. My height is 10 because I've got 2 here plus 6 here plus 2 here. So that's 10 cubed over 12. And then let's get this minus 2. This is 2 wide and 6 tall. 2 wide, 6 tall divided by 12. And then I would subtract the other one, but that's why there's a 2 there. And I'm all set. That, to me, seems like an easier than calculating a centroid. Okay, now, for those of you that have paid attention this long, I've got a bonus for you. I know, you're thinking, wow, and this was so good already. Well, I know. Don't tell people about this. I got to get up this other screen here and then make sure that it's recording properly. There you go. All right. So I draw these shapes in Inventor, and then I go to there's 3D model, there's the sketch, that's where I was drawing it. And then I go to tools and I go to measure, and I want region properties. I don't know why it didn't show up there. I want region properties. Now I select a region. So if I select that, well, this is an easy one, right? Base times height cubed. My base is, sorry about that. My base is 1.5. My height is 2. If I cube 2, that gives me 8. 1.5 times 8 gives me 12. Divide that by 12, it should be 1. So if I hit the calculate button, and then let's drag it over here so I can see it a little better. What you're going to see is it's calculating the inertia tensor. I can't draw on this screen, but I can highlight. And you would think that IXX is what we're looking for, but it isn't. That IXX is with respect to the origin. So you got to be careful. Look down here for this one. I calculated it as 1, and you're seeing, sure enough, it's 1. We're good. And now all I had to do is draw the box, and I got the answer. Where this comes into play is this could be really valuable if you had to do an ugly shape like that, because all I have to do, I got to get out of that. I don't want that. I want to click a new shape. Can I unselect that one? I can't. Won't let me unselect. So I'll restart it. And then I go, oh, look at that shape. I want to do that. Calculate that. Gives me the answer. No big deal. Gives me the answer around its centroid. And it tells me where the centroid is, and it shows me where it is graphically. The centroid is here's my origin. And so in the x direction, it's at 0. In the y direction, it's at 0.599. Now, let's go back. Let's go back and do, or not back, but let's do the problem that we just did. Let me sketch, and I'm going to say, look, I'm going to start in this corner. I'm going to go up. I got to go up, over, up, over, up, down, down, down. All right, now I got to slap some dimensions on it. That's 2. That's 6. I gotta drag this line. I add dimension here 2. And if I put constraints on it, which is what I would teach to freshmen, those have constraints. I'm gonna put equals that and that, and I want to put equals that and that, and I got to put a dimension on here of 2, and I got to put a dimension on here of 6. Oh yeah, I guess I already had that. It might be fully defined if I gave it dimensions from right? I would like it fully constrained, and so I want to say that and that are horizontal. I got to do it the other way. I can't do it the way I do it in SolidWorks. Oh, there we go. Okay, that snapped, and then I got to put a dimension from there to there just to keep it off the. Okay, so it is fully constrained, so I've got it drawn correctly. Now, what did we calculate this as? I gotta jump back and forth. I calculated that as. Oh, I didn't quite give you an answer, did I? I've got 6 times 10 to the third. I got 6,000 divided by 12 minus 2 times 6 divided by 6 to the 6 cubed. It's 216 divided by 12 is 18. So that'd be 36 minus 72, right? Minus 72. So 6,000 divided by 12. I'm going to hold on while I get my calculator out. There, I finished that up. Actually, I'm not quite done. There we go. I got to get my screen back so I can see. 6,000 divided by 12. I should have known that. That was 500 because 12 goes into 60. But I locked up. Sorry, didn't think. And then minus the 72, I get 428. Okay, so now let's pull up the inventor. And got a lot of lines on my screen. All right. I'm going to go back to, I've got it drawn. I go back to tools. No, sorry. Oh, there you go. Look. Under tools, there's measure. Under inspect, there's region properties. Select the region, hit calculate. And there, which is maybe behind my face. Yeah, that's close. There is the answer, 428. So we did it by hand pretty easily because this actually is an easy shape when you're creative. If you would go and find centroids, it'd be a mess. But it was pretty easy. And then you got all kinds of other information about it. And so it's, again, showing you where the centroid is. And it's drawn. Remember, we drew this 6. So you'd expect that to be another 3 over. And sure enough, the x is 9. And the height is 5 because it's 10 tall. So that all works out. And then our values are down here for the centroids of areas for those things. Last thing I'll point it out for you guys only because you stuck through to the end. Again, look at, while it's 10 tall and 6 wide, look at the difference in the section modulus, that second moment. between the x-axis and the y-axis, it is huge, and part of that is, well, it's because it's 10 tall and it's only 6 wide, but it's also because we put our areas at the top and bottom, which really accentuate that section moment in that direction. So this beam is 6 times stiffer when you try to bend it this way than if you would try to get it left and right. All right? And we'll see that when you do your cantilever beam experiment with a yardstick, you will experience that. So big deal, something to keep track of. So okay, don't tell people about this little bonus in the calculating eye section. We're just going to finish the slide up like this so that when YouTube grabs a screenshot, people think, oh, what was he using Inventor for? No. We're not telling people. It's just us. Okay. You guys have a good morning. I'm going to have a good morning. And I'll talk to you later. See you.